Welcome to today's paper reading. Today's paper is titled, TaskGen, a task-based, memory-infused agentic framework. This paper was published on AR14 by John Chong Min Tan and colleagues from Symbian AI and National University of Singapore. TaskGen is an innovative agentic framework designed to tackle arbitrary tasks by breaking them down into manageable subtasks. Each subtask is assigned to an equipped function or another agent for execution. To enhance efficiency, TaskGen employs StrictJSON to ensure structured output from the large language model, along with features like type checking and iterative error correction. The framework's philosophy emphasizes the management of information on a need-to-know basis. TaskGen's effectiveness has been empirically validated across various environments, including dynamic maze navigation, text world escape rooms, and web browsing tasks. TaskGen is an open-source agentic framework designed to break down complex tasks into manageable subtasks. Each subtask is mapped to either an equipped function or an inner agent for execution. Unlike other frameworks that output free text, TaskGen uses a concise JSON format, specifically StrictJSON, which ensures that the output is both concise and easily extractable for downstream tasks. TaskGen also features shared memory, which allows components to share context on a need-to-know basis, and global context, which informs the agent of dynamically changing information. Additionally, TaskGen implements a memory bank that stores various abstraction spaces, enabling the use of retrieval-augmented generation to influence future behavior based on past experiences. Figure 1 provides an overview of the TaskGen framework, highlighting its unique features. First, TaskGen decomposes complex tasks into manageable subtasks, each assigned to an equipped function or inner agent for execution. Unlike other agentic frameworks that produce free-form text, TaskGen employs StrictJSON for each process part, ensuring a concise and extractable JSON output that facilitates downstream tasks. Additionally, TaskGen incorporates shared memory and global context, enabling the agent to adapt to dynamic environments and changing task requirements. These features collectively enhance TaskGen's efficiency and effectiveness in handling complex tasks. The primary motivation behind this research is to develop robust agents capable of solving arbitrary tasks in diverse environments. When faced with an arbitrary task, an agent could potentially perform numerous actions, leading to a multitude of possible outcomes, as illustrated in Figure 2. This complexity makes it intractable for any agent to manage effectively. Therefore, it is essential to limit the scope of what the agent can do to enhance robustness. This limitation is achieved by equipping the agent with relevant functions, which help filter the vast action space into a more manageable form. Additionally, these equipped functions allow the agent to break down complex tasks into smaller, more manageable subtasks, each of which can be solved entirely by one equipped function, as shown in Figure 3. For even more complex tasks, another agent, referred to as an inner agent, can be assigned as an equipped function. This approach increases the processing capability of the agent, similar to how a manager distributes tasks among workers with specialized skills. To ensure these inner agents can perform their tasks effectively, a shared memory system is implemented, providing context and coordination among the meta agent, equipped functions, and inner agents, as depicted in Figure 4. Figure 2 illustrates the intractable action space encountered when attempting to solve an arbitrary task. This complexity makes it difficult for any agent to manage effectively. To create more robust agents, it is essential to limit the scope of what the agent can do. This limitation is achieved by equipping the agent with only relevant functions, which helps to filter the vast action space into a more manageable and tractable form. Additionally, these equipped functions allow for the breakdown of potentially complicated tasks into smaller, more digestible subtasks, each of which can be addressed entirely by a single equipped function. This approach is depicted in Figure 3. Figure 3 illustrates the concept of constraining action space through the use of equipped functions. For more complex tasks, an additional agent, referred to as the inner agent, can be employed as the equipped function. This setup is analogous to a manager delegating tasks to workers, each with their own expertise. By integrating intelligent inner agents as equipped functions, the system can handle more intricate tasks effectively. Figure 4 illustrates how assigning inner agents as equipped functions to a meta agent enhances processing capability. Each inner agent performs a subset of the entire task independently, necessitating a shared memory to manage subtasks completed and shared variables. This setup allows for increased processing capability and coordination among the agents. TaskGen's design philosophy is centered around three key principles. Firstly, the output of each agent or equipped function is designed to be as concise as possible using StrictJSON. This structured format reduces verbosity, cutting down on latency and costs, and improving the reliability of extracting necessary output fields. Secondly, each subtask is mapped to exactly one equipped function or inner agent to guarantee executability and prevent infinite loops. This is achieved through hierarchical execution rules and context-specific assignments. Lastly, information is shared on a need-to-know basis, using a shared memory pool but exposing only relevant information to each agent or equipped function, thereby reducing context length and cognitive load. The core of TaskGen revolves around the definition of an agent, which includes an agent name, a detailed agent description, and a list of equipped functions. These functions can be either internal, which use an LLM for processing, or external, which utilize Python functions for more reliable tasks. The agent's ability to choose the next subtask is crucial, achieved through a two-step process involving chain-of-thought prompting for subtask selection and StrictJSON for input parameter validation. TaskGen is designed to be user-friendly, allowing any new user to learn it within just 5 minutes. The first step is to install TaskGen using pip install TaskGen AI. Next, define the language learning model, LLM, which takes user and system prompts as Python strings and returns the LLM-generated response. Then, define an agent by creating an agent class with a name, description, and integrating the LLM. To enhance the agent's capabilities, equip it with functions using agent.assign_functions, fn_1, fn_2. This allows the agent to perform a variety of tasks. Once equipped, run the agent with a specific task using agent.run task. Finally, query the agent about the subtasks completed using agent.reply_user query to get detailed responses. TaskGen emphasizes concise output, which is achieved through the use of JSON formats. Compared to free text, JSON provides less verbose output, as seen in Figure 5. This conciseness is due to the pre-training data of JSON being more concise without extensive explanations. Additionally, TaskGen employs StrictJSON, which significantly reduces the number of tokens needed to express a schema, as illustrated in Figure 6. This efficiency is crucial for maintaining performance in large systems. The modular design of TaskGen ensures that each component receives only the necessary context, thereby reducing the overall context length for LLM prompts and improving performance. TaskGen's design philosophy includes the use of shared memory to share information on a need-to-know basis. This involves two types of shared memory, subtasks completed and shared variables, as depicted in Figure 7. Global context is another feature that allows persistent variables to be carried through tasks, providing the agent with the current state in a dynamically changing environment. The memory bank is designed to store information at multiple levels of abstraction, which is essential for a generic problem solver. This approach enables task-augmented prompting and equipped function filtering by task, enhancing LLM performance by ensuring the correct functions are utilized. TaskGen also offers additional features such as a conversable agent, which provides a two-person chat interface where the agent can perform actions using its equipped functions and interact with the user. The system includes an inbuilt code generator and code corrector, which can execute actions using Python code, similar to Codact. For faster processing, TaskGen supports asynchronous mode, offering equivalents for strict_JSON, function, and agent classes. These features collectively enhance the versatility and efficiency of TaskGen in various applications. Figure 5 illustrates the difference in conciseness between JSON and free text outputs when using GPT 3.5 Turbo. The figure demonstrates that JSON format generally yields less verbose output compared to free text, even when given the same input prompt. This example, dated July 12, 2024, highlights the efficiency of JSON in reducing the length of LLM outputs, which is crucial for minimizing token use and improving system performance. Figure 6 illustrates the difference in verbosity between StrictJSON schema and JSON schema. The StrictJSON schema, depicted at the bottom, is significantly less verbose compared to the JSON schema shown at the top. The token count for both schemas is computed using the GPT 3.5 Turbo Tokenizer, highlighting that StrictJSON can express the entire JSON schema with fewer tokens. This reduction in verbosity is particularly beneficial for systems like TaskGen, which avoids the typical JSON schema approach due to its excessive verbosity, opting instead for the more concise StrictJSON schema. Figure 7 illustrates the two types of shared memory used in TaskGen to facilitate information sharing between the agent and equipped functions/inner agents. The first type, subtask completed, is a Python dictionary that stores the outcome of each subtask. The dictionary key is the name of the equipped function/inner agent and its input parameters, with the value being the function output. This past history of function inputs and outputs is made known to all LLM-based components of the system to help with shared awareness. Notably, this approach differs from the traditional React framework by not storing the earlier thoughts, which empirically has been found to be sufficient for the LLM to understand past history and make informed decisions while reducing context length. The second type, shared variables, is also a Python dictionary that stores Python variables. These variables are made available to the agent and all equipped functions/inner agents upon request. The exact names and values of these shared variables are not included in the prompt to LLM calls by default, meaning this information does not increase context length unless explicitly referred to. This allows for the storage of lengthy text output as well as file names for various modalities for suitable pre-processing when needed later on. The equipped functions/inner agents are also allowed to modify these shared variables, directly updating the shared memory whenever necessary. In this section, we evaluate TaskGen across multiple environments to demonstrate its versatility. Firstly, we examine dynamic maze navigation, detailed in Appendix D, where TaskGen is tested for its ability to navigate complex, changing mazes. Secondly, we look at escape room solving within the text world environment, as described in Appendix E, showcasing TaskGen's problem-solving capabilities in interactive text-based scenarios. Lastly, we explore web browsing, covered in Appendix F, where TaskGen is applied to navigate and interact with web pages, further illustrating its broad applicability. Continuing our evaluation, we turn to the math dataset, as detailed in Appendix G, where TaskGen is assessed on its ability to handle mathematical tasks. This section highlights TaskGen's capability in processing and solving mathematical problems. Finally, we evaluate TaskGen in a RAG-based question answering (QA) scenario using the natural questions dataset, as described in Appendix H. This part of the evaluation demonstrates TaskGen's effectiveness in answering complex questions, further underscoring its versatility across different domains. In the dynamic maze navigation task, TaskGen, utilizing global context and an external StrictJSON planner, achieved a 100% success rate on the first try, even after the environment changed. For escape room solving in text world, TaskGen outperformed a neural network agent, achieving a 96% solve rate when dense rewards and detailed goals were provided, and an 88% solve rate when commands needed to be derived by the agent. In the web browsing agent scenario, TaskGen successfully completed 69% of actions, simulating real-world tasks such as searching for academic studies, gathering news headlines, and summarizing market trends. On the math dataset, TaskGen with equipped functions achieved an average accuracy of 71% on challenging Level 5 problems, significantly outperforming the 44% accuracy of the agent without these functions. This highlights the importance of code generation and debugging capabilities in problem solving. In RAG-based QA on the natural questions dataset, TaskGen's interactive retrieval feature outperformed the baseline LLM with RAG across all metrics, achieving an F1 score of 47.03%, precision of 40.75%, and recall of 55.59%. This demonstrates TaskGen's effectiveness in dynamically refining context for more accurate question answering. TaskGen is currently in production at Symbian AI, demonstrating its effectiveness by focusing directly on task solving rather than relying on conversation. This approach represents a significant improvement over many existing agentic frameworks. Moving forward, TaskGen will undergo active development, with future enhancements including improved planning capabilities through state-based graphs and parallel searching, integration of multiple memory abstraction spaces like vector databases and knowledge graphs, and the use of reflection to consolidate experiences for better decision-making. Additionally, TaskGen will expand its multimodal support and facilitate collaboration among multiple agents with diverse skills and biases. The concept of hybrid workflows, which mix fixed processes with flexible agentic selections, will also be explored and integrated into TaskGen, potentially using StrictJSON or fixed rules for dynamic routing over TaskGen agents. The TaskGen framework is currently under active development and is open to contributions, inputs, and feedback from the community. Collaboration is facilitated through our GitHub repository, where you can contribute directly to the project. Additionally, a Discord discussion group is available for more interactive engagement and real-time discussions. By participating, you can help shape the future of TaskGen and contribute to its ongoing evolution. For detailed information on the Community Contributions Experiment, refer to Appendix C. Contact Hardik at hardik121998@gmail.com for further inquiries. For the Dynamic Maze Navigation Experiment, see Appendix D. Contact John Tan Chong Min directly for more details. Regarding the Text World Experiment, consult Appendix E. Richard Cottrell is the contact person for this experiment. For the Web Browsing Agents Experiment, details can be found in Appendix F. Contact Brian Lemishing for additional information. The Math Dataset Experiment is detailed in Appendix G. Bharat Runwal can be reached at bharat.runwal@symbian.ai. Finally, for the Natural Questions QA Experiment, refer to Appendix H. Contact Prince Saroj for further details. Thank you for watching.